Today, I'm going to talk about the kind of a little bit step back a little bit kind of on the market perspective of neuromorphic computing. Kind of what do we need to do to raise our, kind of impact to the broader computing world, and use an example of something and discuss an example of something that I actually talked about at NICE, I think it was 3 years ago, when we could meet in person, up at Intel. It's kind of put a bow on that story I kind of introduced a few years ago, and how this might be useful for computing at large. So the sort of initial example it's worth kind of looming in the background of any neuromorphic talk is quantum computing. Quantum is very successful. Not necessarily, their technologies are 20 years down the road in a lot of cases, but they're showing immediate results today that are high profile and getting people excited, and they have a kind of clear story to the world of why it is that quantum computing is the future. And part of that is they have a notion, a computational complexity notion of quantum supremacy. And it's a fairly loaded concept, but in the end, it kind of provides a formal benchmark where it's like, okay, if you can build this, you will be better than a conventional computer. For the certain sort of tasks, or maybe all tasks, right? And so we don't have the equivalent for neuromorphic. We have some ideas. We talk about that a lot, but we don't have the sort of concrete neuromorphic supremacy example, and it's arguable whether that even makes sense. So I want to talk, introduce the concept of a neuromorphic advantage, and the idea being that, where is it that a neuromorphic hardware is going to distinguish itself from GPUs and CPUs and other kind of off-the-shelf technologies today, the FPGAs you just heard in the last talk, for instance. And if you think about the, sort of two axes that we care about, for a general user, is how fast it is and how energy efficient it is. Operations per joule and operations per second. And if you have a technology that's kind of sitting in this sort of bottom left part of this graph, it's, I have stick some algorithm on neuromorphic hardware, and it's slower and more energy costly, no one's going to use it. It doesn't make any sense. But you can see that, there's, if you look across these technologies, there is kind of a trade-off between speed and time. And so if we think about neuromorphic, if you can do something today that sits outside of that bottom left, maybe on the above or to the right of it, and we know that neuromorphic is only continuing to get better. It's an immature technology, there's a lot of opportunities. Then we can say that we have a clear path to an advantage. We're sitting out here. So we define for our purposes a neuromorphic advantage as an algorithm that is already advantageous on one of these axes, such as time or energy, and has strong scaling implications for the other axis. Basically, is there a path on this algorithm on neuromorphic hardware to make it to the top right? Just a little bit of context setting. I'm not going to go too much into this, but we're focused right now on the sort of big platforms today, things like the big Loihi systems or the big Spinnaker systems, the Brainscale systems that we've been hearing about. This is not to dismiss the future of analog and crossbar sort of technologies or more exotic dynamical architectures and so forth. It's just that's coming in the future. We want to think about, are the things today advantageous? So focus on spiking neuromorphic. And we really want to compare to, GPUs. And the reason is that if you look at how the, kind of moving from CPUs to ASICs, there's a concept in optimization theory called no free lunch, which is you can make something better along one axis, but it doesn't get better on all axes. Otherwise, that'd be your baseline, effectively. And so CPUs are kind of universally good at most things. ASICs are only good at one thing. And GPUs kind of sit somewhere in the middle. And we actually would say that neuromorphic should similarly sit in the middle. We think it'll be good at some things and not as good at other things. And so it's easy to get kind of caught up on, okay, let's compare a neuromorphic system to a CPU, or compare it to some specialized accelerator on the right. Really, it's GPUs that we want to understand. Can neuromorphic compete with GPUs? So the problem is, so then the question is, what do we want to explore this on? And so everyone talks a lot about deep learning. I mean, it's trendy, it's the thing to do. And part of it with neuromorphic is that you can say, well, deep learning seems to fit these architectures. They're neural inspired. Deep learning is neural inspired. But the problem is not that deep learning is not good at neuromorphic, and we've been working out how to do that, of course, like everyone, but it's also really good at other things. GPUs are really good at deep learning, and it's not surprising because deep learning evolved to be good at GPUs. That was the sort of system, the ecosystem that those algorithms were developed in. There's another problem, which I think is more complicated. Maybe we can get Neuromorphic to do better than a GPU at deep learning if we spend a ton of money on it. But we're not going to do better than some of these specialized systolic array accelerators on deep learning. This basically, someone builds an ASIC to do deep learning at really low power and really, really fast, and that's the only thing it's going to do. It's going to be hard for something that's programmable and general purpose using fairly conventional fabrication technologies to beat that. I don't know why there's a V there, but okay. So where should we look at? So the first thing we could look at is something that's not necessarily in the middle of sort of well-established tasks. We can kind of think about things that are more brain-inspired. The last talk was a fantastic example of kind of, let's move a little bit outside of what everyone does with computers and think about what an algorithm should look like if it's brain-inspired. And this is obviously the way we want to go. There's no reason not to do this. I think this is what's exciting. NICE as a conference was premised on this point, really. But there are some complications here. The first is, if you do that, you have to create a market. You have to convince people to take this approach to computation. So now you have risk on the hardware and the algorithm side. And that's fine. I mean, that's where opportunities come from. But that's just something to pay attention to. The second issue is that we're going to find out that GPUs and some of these accelerators, in some cases, might actually be really good at these things we discover. And again, that's not a failure. If we come up with an algorithm that kind of does cognition brain-like way, inspired by neuromorphic, but it is wonderful on GPUs, that's a huge win. But it doesn't make the neuromorphic story a lot any easier to say. So what we thought would be good to do is think about what sits in this, in these sort of opportunities, where we look at what is it that a GPU or a similar sort of multi-purpose specialized architectures have trouble with that we can actually do really well at on neuromorphic hardware. So this is kind of the opposite approach. It's not going towards what the brain does, but rather let's think about what people use computers for that GPUs aren't helping that much. So there's a reason to do this more than just, go neuromorphic, yay. And you can look at it when you look at the the trajectories of the supercomputer industry in the last few years. There's been a lot of push towards exascale computing, which is having the next milestone in bigger and bigger HPC systems. And in order to get there, we had to have, the HPC community had to have strong advances in terms of energy efficiency for understandable reasons. And to do this, they've leaned a lot into using GPUs for this purpose. So the biggest systems today use GPUs. They're kind of a co-processor along with CPUs, kind of historic, workhorse of HPC systems. But the problem with this is that GPUs, again, like I was talking about, if they were good at everything, you'd only use GPUs in a system. They're not good at everything. And if you're doing big partial differential equation physics simulations, which is why you build supercomputers by and large, there are going to be some things that are outside of what GPUs are good at. One of those categories of things is using Monte Carlo simulations to solve certain PDEs. And I'll kind of unpack this in a second. But there's a lot of big supercomputer simulations do Monte Carlo, which is a lot of random sampling simulations that are kind of in parallel, and they run those to approximate very complex high-dimensional functions. And these generally aren't that good at GPUs. And what we would like to do is see if neuromorphic can actually hit on this. Right? Can neuromorphic address this gap in the growing gap in the numerical computing community? That one challenge is that, so if we're talking about what is it PDE solutions do, what Monte Carlo can do, when we could think about this class of algorithms as things that kind of rely on diffusion under the hood. So deep down, things like molecular dynamics, radiation transport, a lot of finance modeling. These are often pretty heavily dependent on the diffusion equation, which is a fairly simple physics equation that think most of you probably are familiar with. Let's see, so this is what we kind of showed a few years ago at Hillsborough, is that you can actually build a neuromorphic algorithm using spiking neurons, simple leaky integrated fire neurons, to do diffusion on a chip, and it works very efficiently, and fairly sophisticated circuit. But in effect, what we're doing is we create the state space for these neurons to evolve over on the neuromorphic chip, and the spikes moving over the hardware effectively are the random walks, sort of the stochastic process evolving on that hardware. So then you average over that, how many walkers are at each location of the state space, and that's your sort of Monte Carlo solution. So if you do this task, you see a fairly definitive neuromorphic advantage, as we described above. It is very much energy efficient, and so number of walker updates per joule is much higher on both the Intel Loihi platform and on the True North platform, and there's no reason to think it wouldn't be high on all the other neuromorphic platforms as well. There are some there's some subtleties here, right? IBM, the True North chip is very, very energy efficient. It goes a lot slower. Loihi is kind of almost as fast, actually, as a straight CPU on this task. GPUs are very fast on this in the simple version of this, but we suspect they actually don't scale well at all as the system gets more complex, and you lose that energy efficiency, obviously, with GPUs. So this is a clear neuromorphic advantage for simple random walks, Brownian motion over a mesh. And I'm not going to go into this, but this is effectively the class of PDEs that you can solve by putting them on these hardware platforms. I'll unpack. So basically, the issue is we wanted to do these stochastic processes. So if you go here on the stochastic process, this is the random walk, and if I can simulate that random walk, I can solve these complex problems. So this is diffusion. I'm just looking at only a couple terms. This would be one with diffusion drift. This is one with having jumps periodically in there. This is one with very big jumps. These are all done on Loihi. They're all done by simply configuring your mesh to allow more complex movements of random walks over the algorithm space. And so there's no additional cost of having the more expensive, more complex random walks. It's just, I'm just going to have connections there. And it works. And this is, you can have walkers die and so forth, super diffusion and so forth. So what can we actually do with this? So the first thing we can do is, we can look at simple like physics, Boltzmann dynamics sort of things, right? Where I have particles that might have a direction, like a spin direction or so forth, and they can, flip between one state, like a +1 and a -1 state, get absorbed. This is a simple particle physics example. And this example, we can just do with a handful of neurons. It's a 2-state model, really a 3-state model with the absorption. And we show on, I think this is True North examples. We can do a bunch of random walks basically immediately on this simple example, and we can get the analytical, we approach the analytical solution very effectively. So this is doing particle physics now on True North. Here's another particle physics problem. This is one where you can imagine a particle moving along some trajectory, and it, think of someone taking an X-ray of a bone, for instance, and the particle scatters at some location in space, and the particle reflects, and its velocity is preserved, its overall velocity, but its velocity in the x dimension is going to be a function of the angle. And so we can do this. We did this on Loihi, and Loihi is doing what you get in MATLAB, and it approaches the MATLAB solutions as you would expect. This is looking at more complex geometries. What we can do is we can do simulations on a, not just Euclidean space, but we can do any graph. This is on spheres, on barbells. The bottom left is on the sphere examples, actually on Loihi. The little weird line you see there is just the meshing effects of trying to do a surface diffusion on the surface of a sphere. The Loihi is doing exactly what you would expect it to do on any platform. So we can get complex geometries, we can do complex tasks. There's a very large range of them, of course. So what is the issue, right? I mean, this is something that is much more, it's energy efficient. It seems to be faster. What's the catch? And the issue, I think, here is what we see with any Monte Carlo simulation. Monte Carlo simulations are a function of how many of these stochastic processes you average over. The accuracy converges, fairly inefficiently. You have to have a lot of walkers in order to converge on the right answer, which is shown in the top line here. And that's the case if you do any implementation, whether you're using random walks on GPUs or random walks on Neuromorphic. And similarly, you have to discretize time. Time is not continuous, and that's the same sort of challenge. But if you're on neuromorphic hardware, we get additional things, right? We're not building meshes with floating point precision between the state spaces. So we end up discretizing space in a more coarse way by necessity than if you are just updating your position with a 32-bit number, for instance. For some applications, that's going to be a game, deal breaker. For other applications, it doesn't matter at all. Sometimes you have quantized state spaces. If you're doing random walk over a graph of some sort that's predefined, this isn't going to be an issue. And then finally, one that's I think particularly interesting to this crowd is that there are hardware-specific things like the precision of random number generators on these chips, which you can often algorithmically engineer around those limitations. But it is a challenge when you have 8-bit random numbers and you're trying to do fairly complex random walks. And so we actually explored a little bit of this. I'm not going to go into detail. This is the circuit that we use on Loihi to do which random path does a walker take. And we're limited by basically 8-bit random numbers on the Loihi neurons, at least in our implementation. And what we can do in simulation now, we go into MATLAB and we can artificially kind of change the transition probabilities that we have in MATLAB. And that MATLAB simulation actually, if you have like a 7-bit simulation you're seeing here, the 7-bit simulation in MATLAB matches the sort of kind of error trajectory that we see on the Loihi chip. So that's saying that we're getting the equivalent of a 7-bit simulation out of Loihi, which is pretty good actually, given that we're at, know that our limitation is 8-bit random number generators. So it seems like we're able to capture at least 50% of the precision that's available to us on the Loihi chip. So just to wrap things up, we showed that we're very confident in this now, that there is this class of PDEs that make neuromorphic quite attractive for large-scale scientific computing applications, in particular, sort of things that are based on the diffusion equation. And that this is something that GPUs are not going to be very good at. So it's an opportunity for our community to make impact there. I would also, I'm not going to go into it, but I would say that, what does this red bar here really mean? And I'd say this is anything that is going over large graphs. Neuromorphic hardware is naturally a graph processor. GPUs are very much not. And so I think that's a way to think about this. So with that, I want to just thank the people that worked on this project, as well as the folks at Intel and IBM True North team who've arranged for us to have the hardware through Lawrence Livermore and Sandia. And our funding sources. Thank you very much. I apologize for the noise.
Thank you. No problem. Thank you, Brett. I think attention trick work, so it was fine then. Thanks. Excellent talk. We have a couple questions. I will read one that